Hello everyone. Let's continue our discussion on understanding how the glitch width is important. Okay, so what we have done is we have taken an inverter and we have connected an output capacitance to the inverter. And when we give this rise pulse at the input of the inverter, we get the output something like this. And the 50 to 50, 50 to and the 50% to 50% distance is referred to as the propagation delay of this particular inverter. Okay, so that's what we have mentioned over here. The TPD is the propagation delay of the inverter, and it's called as T2 minus T1. Now, what we'll do is we'll try to increase the output load. We'll do a step-by-step understanding of how the glitch width over here is important while considering the noise. So the second step that we'll be doing is we'll try to increase the output capacitance, okay, and see what is the impact on the waveform. Let's do that. So you increase the out. We have claimed that the propagation delay increases as the output load increases. Let's try to look into that. So once you increase the output load, you will see a variation in the transition at the output of this particular inverter. You see that if you increase the output capacitance, the slew moves and your propagation delay of this particular inverter increases. It's still T2 minus T1. It still lies between the center point of this particular waveform minus the center point of this particular waveform. So the propagation delay calculation will still remain the same, but you see the propagation delay increases. Let's try to increase it further. If you increase the capacitance even more, you see a propagation delay increases. But there is one important thing to notice over here is, even though you increase the capacitance, even though you do all kinds of things to increase the propagation delay, the moment or the point at which the inverter responds, that point is this one. So basically any signal which comes at the input of this particular inverter, the inverter needs at least T3 minus T1. Let's give it some name. Let's call it D. So the inverter needs at least D amount of time to respond to any input signal which is coming on its way. Okay, so in that case it's very the analysis is pretty simple, that any input which is coming at the input of any signal that is coming at the input of the inverter or any logic gate needs at least D amount of time for the inverter to get respond for the inverter to respond, which means the glitch width that we're talking about, that should be at least D, so that it could be identified as glitch on the next cycle, on the next stage. So let's look into what happens when we use this as an input. Okay, so what we say is if the glitch width is less than D, it does not propagate through the inverter. Let's try to diagrammatically look into this into this particular behavior. We'll draw one more timeline over here, and we'll expand this particular lines for T1, T2 and T3 and place this glitch over here. Okay, so the glitch starts at this point. You see the edge, the rising edge of this particular glitch coming at this point. So center 50% will be this point, and this particular inverter to respond to this particular glitch will need at least D amount of time. Okay, but what we see over here is the glitch dies out even very much before the D time period. So due to that, what happens, this particular glitch with a very small width is not even recognized by this particular inverter. So this glitch, even though it crosses the DC noise margin, or basically even though the glitch height crosses the margin that we have, because of it having a very low width, it gets absorbed by this particular inverter. So basically this inverter acts like a low pass filter. It will just ignore all the high frequencies, and it will allow only the low frequency signal to pass through it. This pulse is a very high frequency pulse, and as a result of that, this particular inverter doesn't allow this particular pulse to pass through it. And the reason why it is a low pass filter is if you see, the minimum amount of time required for this particular inverter to respond is D. So it needs, and if you just invert D, 1 by D will be your frequency, which is a very low over here. That's why it's a low pass filter. And this particular D, this particular glitch width, if you see, and if you invert that 1 by this particular width will give you a frequency, and this is a signal of very high frequency. So, and the high frequency signals are getting blocked by this particular inverter. It's just because the response time of the inverter is minimum D. Okay. So T1 minus T4 minus T1 is your glitch width. Inverter will not be able to respond to this, but inverter will be able to respond to this edge, but again, it will respond only after a time period, only after a certain time period D. And after that the glitch dies out. The glitch dies out before D, and as a result of that, you see the glitch doesn't get propagated. So there will be no change in the output. This glitch is a basically safe glitch, you can say. Okay, so now let's try to put this in the chart that we already had. We had a chart for noise. Basically we had a noise chart. We had a DC noise margin level over here. We had this noise height. We had this axis for noise height. We had this axis for noise width. So basically this was the DC noise margin, which said that any glitch whose potential or whose voltage is below this DC noise margin, those are called as safe glitches. And any noise whose voltage whose glitch voltage level is more than the DC noise margin, those are unsafe. Those are safe. Those are unsafe glitches. But now in the experiment that we did just now, we saw that it is not only a function of noise height, but also a function of noise width. So now we have a signal, we have something called as, we have a time varying function over here. Okay, so safe glitches definition will now change. It's not only this particular, it's not only for the signals which are below this particular DC noise margin, but there is something else to add to it. So let's add that things over here. So safe glitches are also are a function of noise height and noise width as well. Just summarizing things over here. So let's draw it. So we have, let's say we have this particular curve that we have drawn over here, and we decide that anything which if the noise width lies somewhere over here, if the noise width is this high, let's draw it. Basically this will be safe. So whatever you see over here, if your noise height is lies somewhere over here, but your width lies somewhere over here, you still consider it as a safe glitch. Okay, so this will be now your noise rejection region, where you call all your glitches which lie in this area will be called as your safe glitches. Now for example, if you have a glitch which is of this height and which is of this width, so eventually if you see the width of this particular glitch is crossing the AC noise margin, so that will be considered as an unsafe glitch. Okay, so let's draw the color the area for unsafe glitch as well. So anything which is lying in this area, any waveform, any glitch waveform which lies in this area will be called as potentially unsafe glitches, and anything which is lying in this area will be called as potentially safe glitches. So if you see something, if you see let's say a waveform like this, okay, it crosses the DC noise margin, and it also crosses the AC noise margin because the waveform, the noise width is much greater than what you see over here. So those will fall in this category, and we call them as potentially unsafe glitches. So what we'll do is this, since this particular graph is varying with respect to time as well, it will be called as AC noise margin, AC noise rejection ratio. So what we'll do is we have to look into some of the examples with this particular graph. So we'll try to take some examples with this particular graph, and let's say we'll try to understand or deep dive more into glitches. So let's try to do all this in the next video. Thank you.